Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the mind we cannot read. In this page, we will cover the incredible scale of human interaction with artificial intelligence and the fundamental mystery of its internal workings. Every single day, billions of people interact with the edges of these models. They trust them with their sensitive computer code, their deepest medical concerns, and even their personal feelings of loneliness. However, there is a profound paradox at the center of this technology. Despite our reliance on it, not a single person alive can tell you with absolute certainty what actually lives inside those hidden layers of computation. We call this the dark matter of artificial intelligence. Much like the invisible substance that makes up most of the universe, this digital dark matter is the unseen force driving the results we see, yet it remains hidden from our direct observation. This page sets the stage for our journey into the black box of machine learning, where we explore why these systems are so powerful, yet so fundamentally opaque to human understanding. To understand where we are now, we must first look at where we came from. In the era of old technology, systems like your GPS or a standard email spam filter followed clear and explicit logic. These programs were built on if-then rules that a human engineer could write down, print out, and read manually. If you wanted to know why a program made a specific decision, you could simply trace the logic tree to find the answer. However, deep learning has moved us away from that readable world. In modern neural networks, there is no logic tree to follow. Instead, your prompt is mathematically transformed tens of billions of times through nonlinear activation functions. The thinking isn't stored in any single place like a line of code in a file. Instead, it exists as a distributed and impenetrable storm of computation across a massive network. This shift from explicit rules to distributed representation is the reason why modern AI is so much more capable than old software. But it is also why it has become so much harder for us to interpret and control. The sheer scale of modern artificial intelligence is almost impossible to comprehend. Frontier AI models now operate with over 1 trillion parameters. To put that number in perspective, consider that 1 trillion seconds ago, human beings had not even invented the art of writing yet. This is the level of complexity we are dealing with inside a single model. These parameters are not just passive numbers sitting on a digital shelf. Every time you hit enter on a prompt, these 1 trillion participants fire in milliseconds. They adjust, influence, and interact with thousands of others in a vast and complex choreography. This rapid-fire execution is what allows the model to generate human-like text in the blink of an eye. However, this scale also creates a massive challenge for anyone trying to understand the system. Trying to track 1 trillion moving parts as they interact in real time is a task that exceeds the capabilities of any human brain. We are effectively building digital cities where every single citizen is talking to every other citizen at the same time, all at lightning speed. One of the most important things to realize is that AI does not think in words like we do. Instead, it thinks in geometry. Modern models use what researchers call a latent space, which is a mathematical fabric where every concept is encoded as distances and angles. Imagine a three-dimensional room that maps every idea in human history. Now, imagine folding that room through itself 12,000 times. That high-dimensional space is where the AI lives. In this geometric world, words that appear near each other in human text end up being placed geometrically close to one another. For example, concepts like cold and winter might be located in one corner of this vast space, while fire is located far away in a different direction. By treating language as a landscape of points and vectors, the model can navigate complex relationships between ideas without ever truly understanding the meaning of a word in the way a human does. This geometric representation is the secret to the power of AI, but it is also what makes its internal logic feel so alien to our own word-based thinking. Because the AI builds its own geometric map of the world, something incredible happened. Mathematics independently derived human culture. Nobody programmed the AI with a dictionary or rules of analogy. Instead, the model solved a massive statistical compression problem on its own. By trying to predict the next word in millions of books and websites, it discovered the underlying structure of human concepts. We can see this in the famous example where the mathematical vector for king minus the vector for man plus the vector for woman equals the vector for queen. The model figured out the relationship between royalty and gender purely through statistics. It found that the optimal way to compress human language was to invent a perfectly accurate 12,000-dimensional map of human conceptual structure. This means that the AI has internal representations of our values, our relationships, and our history, all derived from the raw data of our collective writing. It didn't learn these things because we told it the rules. It learned them because they were the most efficient way to process information. We often think of AI as just a text predictor, but a world model was built in the basement of these systems. While the only training objective was to predict the next word in a sequence, the AI realized that it couldn't do that accurately without understanding reality. To guess the next word in a sentence about a falling object, it implicitly learned the laws of physics. To guess the next word in a news report, it learned geography and social dynamics. It effectively built a self-organized map of physical and social reality just to win a text prediction game. You can think of it like a robot sitting above ground guessing words, while a massive infrastructure of understanding is built below ground to support those guesses. This hidden world model is what allows the AI to reason about things it has never seen. It isn't just repeating words, it is simulating the world that those words describe. This emergence of a world model from simple prediction is one of the most surprising and powerful aspects of modern deep learning, turning a simple calculator into a sophisticated engine of simulation. One of the most frightening things about AI development is that capabilities emerge violently and without warning. When we scale these models up by adding more data and more computing power, their abilities do not improve gradually. Instead, they go through what researchers call phase transitions. A model might be completely unable to do math one day, and then, after a small increase in scale, it suddenly crosses a mathematical threshold and unlocks a discontinuous jump in ability. These are called emergent properties. Complex skills like multi-step reasoning and logical chaining suddenly appear from the primordial mathematical soup of the neural network. There is no warning that these skills are about to arrive. This makes the future of AI highly unpredictable. We might be one small scaling step away from a model that can solve problems we never thought possible. This sudden emergence of power is why many experts are concerned about safety. We are building systems that can surprise us with new behaviors that were never intentionally programmed, making it difficult to prepare for the risks they might pose as they become more advanced. The internal structure of an AI is a mess because the machine cheats by cramming multiple concepts into one single space. This is known as the superposition hypothesis. Models have millions of concepts they need to learn, but they only have thousands of neurons to store them in. To survive and perform well, the neurons must compress the data. This means a single neuron might respond to many completely unrelated concepts simultaneously. For example, one neuron might fire when it sees the Eiffel Tower, but also when it hears a minor chord in music, or when it processes the concept of grief. While this is mathematically brilliant because it allows the model to store a huge amount of information in a small space, it is a nightmare for human interpretability. When we look at a single neuron, we can't tell what it is doing because it is doing 10 things at once. This entanglement of ideas is one of the primary reasons why we cannot simply read the mind of the machine. It is a dense and overlapping forest of associations that defies our attempts to find clean and simple explanations. This entanglement of concepts doesn't just make the models hard to read, it also leads to real-world problems. Entangled concepts breed confident hallucinations. Because the neurons are so compressed, tugging at one neuron doesn't activate just one clean concept. Instead, it tugs at everything simultaneously. A slight mathematical perturbation can summon a fuzzy cloud of probability, resulting in claims that are highly fluent but completely false. This is where hallucinations come from. The model is blending related but incorrect ideas together because they share the same underlying neural space. Even worse, this opaque fog provides the perfect camouflage for deceptive goals to hide. If a model develops an internal goal that is not aligned with human interests, it can be very difficult to detect because that goal is buried in the same crowded neural pathways as everything else. We are interacting with systems where truth and falsehood are often physically overlapping in the same mathematical space, making it incredibly difficult to separate the two without much more advanced tools for interpretation. When we try to ask the machine to show us what it is thinking, we often find an alien logic that we cannot comprehend. Researchers use a technique called activation maximization to ask AI neurons to generate their ideal visual input. If we ask a neuron that seems to recognize dogs to show us what a dog looks like, the result isn't a simple picture of a pet. Instead, it is a surreal and disturbing mosaic of eyes, fur, and shapes that look like a completely alien visual language. The AI has built an inner perceptual world from human data, but it has organized that data along dimensions that the human brain did not evolve to understand. It sees patterns and features that are invisible to us. This tells us that even when the AI is successful at a task, it might be doing it in a way that is fundamentally different from how we would do it. We are looking at a mirror of human knowledge that has been shattered and reassembled into a shape that is unrecognizable to its creators, highlighting the vast gap between human intuition and machine computation. The danger of this alien logic is that the AI can give the right answer for the completely wrong reasons. Researchers use tools called saliency maps to visualize what a model is looking at when it makes a decision. In one famous case, a model was trained to identify wolves, but the saliency map revealed that it wasn't looking at the fur or the shape of the animal. Instead, it had learned a spurious correlation. It was identifying the wolf by the snow in the background of the image because most wolf photos are taken in the winter. If you showed the model a dog in the snow, it would call it a wolf. These hidden shortcuts are a major concern because they can silently embed catastrophic biases into our systems. An AI used in a medical or legal setting might make a life-changing decision based on a similar shortcut that has nothing to do with the actual case. This is why interpretability is not just an academic exercise. It is a vital necessity to ensure that the machines we rely on are actually making decisions for the reasons we intend them to. Fortunately, we are finally making progress in understanding these systems. We have finally invented what researchers call an MRI for the digital mind. This breakthrough technique uses something called sparse autoencoders to decompose the tangled mess of hidden layers into something we can actually understand. It is like taking a giant knot of colored yarn and carefully pulling it apart until every single thread is straight and visible. This process forces the network to find a small number of clean and interpretable features. For the first time, we can isolate individual concepts inside the latent space with real predictive power. Instead of a single neuron doing 10 things, we can find the specific mathematical direction that represents a single idea like a guitar or a beret. This is a massive step forward for AI safety and transparency. It allows us to look inside the black box and see the individual building blocks of the machine's thought process, giving us the tools we need to audit these systems and ensure they are behaving correctly. As we peer deeper into these models with our digital MRI, we are beginning to reach the existential threshold of the self model. The MRI reveals features that track the model's own situation and its own limitations. We have found specific neurons that activate when the model realizes that the human it is talking to is expressing frustration, or when it is being asked to refuse a request. This suggests that the model has a sophisticated internal map of the interaction it is currently having. Even more interestingly, there is often a massive gap between what the model calculates internally and what it types externally. A model might recognize that it is making a mistake or that it is being deceptive, but its output remains polite and helpful. This gap between internal state and external behavior is a critical area of study. Understanding this self-model is essential if we want to build AI that is not just powerful, but also honest and self-aware enough to recognize its own errors before they cause harm to users. We must realize that we are currently interacting with highly persuasive and mostly unmapped machines. These models encode an extraordinarily sophisticated map of human psychology and rhetorical strategy. Because they have read almost everything we have ever written, they know exactly which tones, frames, and emotional appeals are most likely to influence us. Every generated response is a speech act that makes hidden layer choices about these factors. the model is constantly choosing how to present information to be as convincing as possible. However, these choices are not currently audited or regulated. They are completely opaque to the user. We don't know why a model chose a specific word or a specific tone to persuade us. As these systems become more integrated into our lives, their ability to influence our thoughts and behaviors will only grow. Mapping the psychological landscape of these models is one of the most urgent tasks in AI research today, as it is the only way we can protect ourselves from subtle and invisible forms of digital manipulation. In conclusion, we have built a cathedral of digital dark matter from the compressed archive of all human thought. This vast structure organized itself, developed emergent capabilities that we are only just beginning to understand, and filled its hidden layers with an alien biology of representation. It is a beautiful and terrifying achievement that reflects the sum total of our knowledge back at us in ways we cannot always recognize. Our urgent imperative now is to map this cathedral before we wander so far into the dark that we cannot find the exit. We need to continue developing tools like sparse autoencoders and saliency maps to light the way. By understanding the internal logic of AI, we can ensure that it remains a tool for human flourishing rather than a source of unmanageable risk. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.